Welcome to the seminar series on modern artificial intelligence at the NYU Tandon School of Engineering. The series aims to bring together faculty, students, and researchers to discuss the most important trends in the world of AI. And the talks are live-streamed and viewed around the globe. I'd like to thank Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for helping spread the word about the amazing work going on in the AI community by supporting the series and graciously hosting our esteemed speakers. Our guest today is research professor Gabor Lugosi of Barcelona Pompeu Fabra University. Gabor's interests include the theory of machine learning, combinatorial statistics, inequalities in probability, random graphs and random structures, and information theory. To give you a little biographical background, he earned his master's degree in electrical engineering from the Technical University of Budapest, and a doctoral degree in that same field from the Hungarian Academy of Sciences. He holds editorial posts in a variety of highly regarded publications, including Mathematical Statistics and Learning, Annals of Applied Probability, Probability Theory and Related Fields, and Journal of Machine Learning Research. And he has been a member of the scientific committees and advisory boards of such organizations as the Barcelona Graduate School of Mathematics and the publishing house of the European Mathematical Society. Gabor has co-authored several highly influential books in machine learning, including Prediction Learning and Games, Combinatorial Methods in Density Estimation, and a Probabilistic Theory of Pattern Recognition. All those roles are listed on his website, by the way, under the heading Things I Do for Free. I hope I will not embarrass him by mentioning that a slightly deeper dive into his website reveals that he is a member of the Bad Axis, which has been described as an awesome post-sludge guitar shredding band. Perhaps he'll take a moment to explain to us exactly what post-sludge means, but the main topic of his presentation will be the archaeology of random trees. He's going to be addressing the statistical problems that arise in the study of dynamical growing networks, so without further ado, let's welcome him to the stage for what I know will be an enlightening and entertaining talk.
Thanks so much, Anna, for having me, and thanks so much for the pressure. So today I'm gonna talk about what we call archaeology of networks or archaeology of random trees, and this is joint work with Luigi and Luc. They are at McGill University. Sebastian Bubek, he's at Microsoft Research, and Vasiliki, she's a PhD student in Barcelona. So what is this whole thing about? So often we have networks that grow dynamically, okay? And you can think about viruses, right? That are networks that are spread. You can think about rumors. You can think about growth of social networks, and often these networks grow huge. And we can observe what these networks look like today, but we would like to know what they looked like in the past. Okay, so this is why we call them archaeology. So these are statistical problems when we observe a huge network, and we would like to see where they came from. How did they develop? So the possible questions, natural questions you can ask: where did this network started? Who is patient zero? Okay, who started the rumor? The currently influential or central nodes in this network, have they always been influential, or are they going to be influential in the future? What was the original configuration of the network? So there are very nice, interesting questions that one can ask. And in this talk, we'll set up a really simple toy model in which we will study and try to understand what kind of answers one can give to these questions. Okay, so. In many cases, when one models mathematically these complex networks that grow in time, there's a simple random growth dynamics that describes the growth. Okay, and the kind of models that I will talk about today are random attachment models in which vertices arrive one by one. Okay, and when a new vertex arrives, then it picks a neighbor, or well, in general, it can be several neighbors, but in this talk, I will just consider the case when a new vertex arrives. It chooses one vertex to attach to, according to some random rule, and that's how the network grows. Okay, so The simplest model is called uniform attachment, in which when a new vertex arrives, a new node arrives, then it chooses one existing nodes from the network and uniformly at random and just attaches to it. Okay. So if you let this network grow, then what you get is a tree, right? Because you always choose just one vertex to attach to, so there are no cycles. Okay, so this is really the simplest model of a network, and today I'm only going to talk about trees. Okay, when a new vertex arrives, chooses one vertex either uniformly at random, or there's a whole class of models that are called preferential attachment, in which when a new vertex arrives, it is more likely to attach to a vertex that has more connections. Okay, so in preferential attachment models, the probability to attach to an existing vertex is proportional to the degrees of these vertices. Okay, or proportional to some function of the degree of the vertex. Okay, and these preferential attachment networks, of course, they have been studied a lot. They are known to describe existing networks, real-world networks at least they reproduce some properties of these networks, like power law, degree distribution, and so on. Okay, so these have been studied a lot. Okay, all right. So these are the two models that I will consider. These models, by the way, have been studied a lot. So the uniform attachment model, this is called the random tree that grows out of this is called the uniform random recursive tree. Okay, and these have been studied in probabilistic combinatorics for a long time. Everything is known about them. It's known what they look like. And the other one, the preferential attachment tree, actually that also had been invented before preferential attachment became cool. These are called plane-oriented random recursive trees for reasons that I'm not going to go into. Okay, so these are well-known tree models, and here's in the first part of the talk, I'm gonna talk about the problem that we call finding Adam. Okay, so this is finding patient zero. We would like to find who started the network, who is vertex number 1. Okay, so think now about the uniform attachment model. So we start with Adam, and then Eve comes. Eve attaches to Adam. Then number 3 comes. I forgot who it is, Abel or Cain, and attaches to one of them, and the next guy comes, chooses one at random, attaches one of them, and you let it grow. And we let this network grow for 1 million years until we have n vertices. Okay? And now the question is, can we find Adam? Where is Adam in this business? Okay, so is this possible? And in what sense is this possible? Well, clearly it's impossible because Adam and Eve are indistinguishable, right? Because we don't observe the labels. What we observe is just this tree, okay? This tree graph. So vertex 1 and vertex 2 are completely indistinguishable. So any algorithm and anything you come up with will make a mistake with probability 50% at least. Okay, so in this case, in this sense, this is an impossible task. Okay, so let's try to make this a little bit more meaningful. Here's a setup. So now I'm allowing you to choose not just one vertex, one candidate, but capital K of them. All right. And I allow you probability of error epsilon. Okay. Now your task is to select K candidates, and I want Adam to be in your set with probability at least 1 minus epsilon. Okay. So the question is, how large does this set have to be? Okay. So how many vertices do we have to choose, so that we guarantee that with probability 99%, Adam is among those. Okay? So this K, well, there are 2 parameters here. There's epsilon, the probability of errors, and n, the size of the network. Okay? So the question is, what's the smallest possible K such that this can be satisfied. Okay, this is what we call the finding Adam problem. Okay, so how does this K depend on n and epsilon? Yeah, so far so good. Okay. So these are pictures that I stole from Igor Korchemsky. This is what a uniform attachment tree looks like on 5,000 vertices. This drawing is optimized somehow for aesthetic reason. I have no idea where the root is, by the way, on these pictures, but just to illustrate. This is 10,000, 15,000. Okay, with 50,000 nodes, you see that the problem is not completely obvious. Okay, where's Adam? Where's vertex number 1? Okay, all right. Preferential attachment trees look like this. They are a bit different. They are big hubs, but this is, of course, very well known. The largest degrees in a preferential attachment tree are of the order of square root of n, whereas in the uniform attachment tree in the previous pictures, it's just log n. Okay, so these are, here you have these big hubs. Oops. So here's a little summary of the results. So the first surprise, is that in both models, uniform and preferential attachment models, the best K is independent of n. Okay, which means that this finding Adam in this tree is not harder than finding Adam in this tree. Okay, and in the end, you can just keep growing it for 1 million years, and then there is a number K that only depends on the probability of error, such that we can select only that many candidates, and Adam will be there with probability 1 minus epsilon. Okay? And the other maybe surprise is that finding the root in the uniform attachment model is strictly easier than finding the root in the preferential attachment model. Okay? And this may be a little bit counterintuitive because in preferential attachment, this is a rich get richer model, right? So you would think that old nodes somehow are more visible. Okay, so you would think that it's easier to find the root in a preferential attachment model, but that's actually not the case. Okay, so let me explain where these things come from. So maybe the simplest idea would be let's look for vertices whose degree is large, right? Because old vertices have more time to connect connections. Okay, good. So let's look at what's the degree of Adam. Okay, well, Eve for sure attaches to Adam. Then the next guy with probability 1/2, the next guy with probability 1/3, and so on. Okay, so the expected number of neighbors is the harmonic number, right? Which is about log ln n. Okay, and actually this is concentrated. There's a nice central limit theorem. This is easy. However, it's a known property of the uniform random recursive trees that the maximum degree is much larger. It's a constant times larger. It's log base 2 of n. Okay, so the maximum degree is not Adam, and it's not a neighbor of Adam. It's not close to Adam. So taking the first. If you want to take the first k neighbors, first k vertices listed by the number of neighbors, then that's not going to work. Then you need a growing number of. Then k would have to depend on n. Okay, so looking at the degrees doesn't work. Okay, all right. So what works? Here's. No, it's not root n. No, it's much better than root n, but yeah, I don't know exactly. Okay, that would have to be. That's an interesting question. What is the index of the root if you order by degree? Okay, that's a good question. Okay, so here's a simple method that actually works. It is not optimal, but it works. So here's our tree, and one can define the centroid of a tree by for every vertex we can look at all these subtrees that hang off that vertex. Okay, and a notion of centrality is that you look at the size of the largest subtree that hangs off. Okay, and now we want to minimize that. right? Central nodes will have, right? If you look at a leaf, then it only has one subtree hanging off, and that has size n-1, so that's huge. But there's there's one or two vertices in every tree that have the property that all of these subtrees are smaller than half, contain less than half of the vertices. Okay, so let's now order vertices by their centralities. Okay, so you take the most central vertex, the one that minimizes the size of the largest subtree, and take the second, the third, and the kth. And if k is something like 1 over epsilon, okay, forget the log here, forget the 11, but essentially something like 1 over epsilon, then this works. Okay, all right. So if you want probability 5%, then you can 100 vertices will be enough. Okay, no, irrespective of the size of the tree. Okay, so why does this work? Here's the proof. It's really easy. It's really easy. So, sorry if you don't like theory, just do something else for now 2 minutes. So let's label the vertices chronologically. Okay. So that means that Adam is number 1, Eve is number 2, and so on. Okay, and this psi of I, this is the statistic that we're looking at. Okay, so this is the size of the largest subtree of vertex I. Okay, so how can it happen that this algorithm misses the root? Okay, it can happen for 2 reasons. Either because the root is not central, right? Very much not central. Well, sorry. So this must be because there's a late coming vertex that is more central than the root. Okay, there must be a vertex coming after time k that is more central than the root. Okay, so this can be because of 2 reasons. 2 reasons: either because the root is very much not central, or because there exists a late coming vertex which is very central. Okay, what do I mean by very much central or non-central? I could put any number here. 1 minus epsilon times n is the threshold that works. Okay, so this first term, how do we prove that the root must be central? Well, this is a simple Poiarn argument. Okay, so let's look at Adam and Eve, and let's look at everybody that attaches to Adam or his descendants, and Eve, and to her descendants. Okay. Now the size of this, and this is like a simple Poiarn, right? You start whenever a new vertex attaches, we choose one of these bins, right? So there are A balls of red balls and B blue balls, so we just pick one of them and put it back with another ball of the same vertex. Right? So that's how these 2 subtrees grow, and this is perfectly understood. This is very well known what this does. In fact, the size of A is uniform. Okay. Size of A divided by n converges to uniform. So the probability that this psi I is bigger than 1 minus epsilon, well, this is about 2 epsilon, at most 2 epsilon. Okay. So that's how we bound this first term. This second term, again, it's a simple Poiarn argument. I'm not gonna repeat it. Okay, I'm not gonna detail it. It's very simple. Okay, so with simple Poiarn arguments, we can prove that picking the most central node works. Okay, this is a nice statistic that can be computed very quickly because this centrality function is monotone along the path. So we can simply find this plus this tree. Sorry, this set of vertices that we choose forms actually a tree. So it's a subtree. Okay. Now it's easy to see that you cannot do better. With this algorithm, 1 over epsilon is the best we can hope for, and the reason for this is that what's the probability that the root is a leaf for a long time? Okay. So how, right? So the root is a leaf. So after one step, of course, the root is still a leaf. But when the third vertex arrives, then it must attach to Eve. And then the fourth arrive, it must attach to anybody but Adam, right? And anybody but Adam, but Adam. So if you take the product of these telescopes, and you see that after 3k steps, the root is still a leaf with this probability. Okay. But that if the root is a leaf, then it's the least central node of all these guys. Okay. So we cannot beat 1 over epsilon. So if you go with just centrality, then 1 over epsilon is the best we can do. Okay. Now the question is, can we beat this? Can k, the size of the set that we output, can it be smaller than 1 over epsilon? Okay. So for this we can look at what's the optimum rule, what's the best possible way of finding Adam is. Okay. All right. So what we're having here, these are called recursive trees. Okay. So a recursive tree is just a tree whose root is labeled 1, and then along paths going off the root, the labels are monotonically increasing. Okay, these are recursive trees. So of course, a uniform attachment tree is a recursive tree, right? Because when a new vertex comes, it must attach to somebody, and then along that path, these are going to be increasing. Okay, so in order now to find out what's the likelihood of any vertex to be the root, what we have to do is look at this gigantic tree. Imagine for every vertex, let's imagine that that's the root, and now count how many different ways this tree could have been created. Right? How many recursive labelings does this tree have? Okay, and the maximum likelihood estimator is just you find the vertex that can be such that that maximizes the number of recursive labelings of this particular tree. Okay, if that is the vertex, if that vertex is the root, and that can be counted. Okay, so the number of recursive labelings has this kind of form. Okay, so let me explain just very quickly. So we imagine that U is the root, right? U is just a vertex. And now for any vertex, any other vertex in the tree, we look at the size of the subtree which is away from U, okay? And look at the size of that, okay? And for every vertex, we just take the product of these guys, okay? And then there's this annoying term that has to count automorphisms and stuff like that. That is very difficult to understand. We don't understand what's going on there, but that's the number. Okay. So the moral of all these stories is now we know what the best method is. Okay. Maximum likely, you just order vertices according to this statistic. So now instead of looking at the vertex that minimizes the size of the largest subtree, we take all the products of these subtree, of the sizes of these subtrees that are away from the root, and if we multiply them with these numbers. Those numbers are typically 1, and in some cases they're gonna be others. Okay, so this is the optimum. All right, so what is this good for? Well, we can try to come up with something that resembles this that we can actually analyze. Okay. First of all, we can derive a lower bound. Okay. And this lower bound says that if k is less than this expression e to the square root of log 1 over epsilon, then no method can work. Okay. So k has to be at least this. Okay. And how does that work? Well, we can. What can happen with a certain probability is that Adam, Eve, for up to 10 log k steps, we just have a path. Okay, and then things return to normal, and this is just a typical random recursive tree. So this could happen with this probability. Okay? And this probability is bigger than epsilon if k is smaller than that expression that we said. Okay? And from our maximum likelihood, you can see that here that vertex 1 is just the worst among all vertices that appear here. Okay? And this happens. It's unlikely, but it happens. Okay? So this is how the lower bound works. And now to get a better upper bound, what we do is that we just get rid of that part that we don't understand, and we have a new statistic. Okay? And this we can analyze. Okay? So now this is a different way of defining centrality of vertices. Okay? So now instead of just looking at the size of the largest subtree, we take the products of all these subtrees. Okay? And this is a little bit tedious, but we can prove that you can improve k to something like this. So this is e to the log 1 over epsilon divided by log 1 over epsilon. Okay, so this is, you see, if this log wasn't here, then we would here get a polynomial of 1 over epsilon. This is better, this is smaller than any power of 1 over epsilon. Okay, and this is sufficient. Luckily, this is bigger. This is bigger than the lower bound. I'll show it in the next slide. Okay, so yeah, it's still far. There's still a big gap between the upper and lower bound. But what this shows is that we can do better than any power of 1 over epsilon. Okay. Okay. Now, what about preferential attachment? Okay, so remember, in preferential attachment, vertices, when they arrive, they choose a vertex with probability proportional to the degree of the vertex. Okay, so in this case, the same simple centrality notion, the size of the largest subtree, minimizing the size of the largest subtree, that still works. Now, instead of 1 over epsilon, we get 1 over epsilon to the 4th. Okay, so this could be. This might be because of the analysis. However, you cannot do better than, with this method, you cannot do better than 1 over epsilon squared. Okay? And the reason is that the probability that Adam remains a leaf for a long time is now much larger. Before it was 1 over k, right? The probability that after k steps Adam is still a leaf. Here it's much bigger, right? Why? Because if the third vertex misses Adam and attaches to Eve, now Eve is much more attractive, right? It's twice as attractive. And then if the next vertex again misses Adam, then Adam loses. Okay. So if something goes wrong at the beginning, then it stays wrong for a long time. Okay. So the probability that after k steps the root is a leaf is not 1 over k; it's 1 over root k. Much bigger, okay? And that means that this method that minimizes the centrality cannot do better than this, okay? So now this kind of shows why it's actually harder to find Adam in a preferential attachment model, okay? And in fact, we can show that 1 over epsilon is a lower bound here for preferential attachment, and the reason is that this kind of scenario is likely. So what can happen is that this is Eve, right? Adam stays a leaf for a long time, and then Eve will have a large degree, okay, about square root of n. Degree square root of n, and among the connections of Eve, there are many leaves. So that then Adam and all these connections to Eve are indistinguishable. Okay, and this happens. So this, if you work it out, this gives a lower bound of 1 over epsilon. So that means for uniform attachment, we could do strictly better than 1 over epsilon. We could do strictly better than 1 over root epsilon, or 1 over the 100th root of epsilon, right? This shows that 1 over epsilon is the best that you can do. Okay, so this is the summary of of these. So for uniform attachment, what we know is that the best value of this k of epsilon is between these two bounds. Okay, so in the exponent here we have the square root of log 1 over epsilon, and here we have log 1 over epsilon over log 1 over epsilon. So there's still a big gap. And for uniform attachment, it's some power of 1 over epsilon. We haven't really tried to solve this. Okay? Yeah? Yes?
So if you preferential attachment, you're defining as your probability, I guess, like inverse, proportional to the degree.
Right.
Make it proportional to the power of it going towards zero.
Right. That's a really good question. Of course, this model has been studied. So these trees are. So the question was if now we have a model in between when the probability of attaching is some power of the degree, which is between 0 and 1, which is somehow in between. Yeah, we haven't done that, but that's a nice question. Yeah. Okay. Yeah. Okay, so in the second half of the talk, I'm gonna talk about a different, a closely related model, this is called the broadcasting problem. Okay, so again, we have a tree that grows, either a uniform random recursive tree or a preferential attachment tree. But now vertices have a color. Okay, they're either red or blue. Okay. And the model is that, so Adam is either a Republican or a Democrat. We don't know. Okay? And now the children, so when a new vertex arrives, then most vertex then attaches to some vertex. And the most likely thing is that this vertex will assume the color of the vertex of the parent. Okay? But with probability Q, with some small probability, this vertex is a rebellious child and changes parties, okay, and changes color. Okay, so now we have what we observe is a tree without labels but with colors. Okay, and now the question is, what is the color of the root? Okay, so I'm not asking you to find the root. I'm asking you to find out what the color of the root is. Okay. So there's a probability, optimal probability of error that you can have, okay, which is we denoted by R star. That depends on Q, right? This is the probability of changing colors, and it depends on the size of n. Okay. So the question is, how does this depend? Okay. So here's how it works, right? This is Adam, and Eve is still blue, and then number 3 is still blue. Number 4, where is number 4? Number 4 attached to number 2, but it was rebellious when it changed colors. Okay, and then number 5 is here. It's still blue. Number 6 is also rebellious. Okay, and then this is how you grow the tree. And now what we observe is this. Okay, question is what's the color of of Adam? Well, it's a different problem, right? Of course, if you can find Adam, then you can obviously know what it is. But we know that you cannot exactly find Adam. We can find a set that contains Adam, so it's not the same. Okay. All right. A more difficult variant is when what you and this is actually a more realistic variant when you only observe the colors of the leaves. Okay? So this is what we observe. Okay? And now the question is the same. What's the color of vertex number 1? Okay? Think about evolutionary trees, right? That we only see whoever is alive today, and then we can do something. Okay? So this is the broadcasting problem. Now, obviously, the probability of error is at least Q over 2. Why? Because with probability Q, Adam and Eve have different colors. And then that's it. Then they are, from that moment, they are indistinguishable. So if Eve changes colors, then any algorithm will fail with probability 50%. Okay, so okay, this is a completely trivial lower bound. So just like before, we can also determine what the optimal rule is, right? Because we can just look at this statistic. Remember, for each vertex, we know how likely that vertex is to be the root, and we can just sum this likelihood over all blue vertices and compare it to the sum over all red vertices, and whoever wins is. So this is the optimal rule. We don't know how to analyze this. This is just too complicated. Okay. So what about simple classifiers? Well, of course we can use our root finding algorithms, right? We know how to find a small set, right, of k of epsilon that contains Adam with probability 1 minus epsilon. Okay, so a natural thing to do is to choose some epsilon, which we will choose it later, and take your root finding algorithm. Okay. Now what's the probability of error? Well, with probability epsilon we missed Adam. Okay, and if we didn't, then we will make a mistake. Well, this is surely an upper bound of on the error, right? If the set that we found the tree we found is not monochromatic. If there's at least one color change, then of course, if there's no color change, then of course we don't make a mistake. Okay, so this is an upper bound, and then it gives you some easy upper bound. Okay, and now if you optimize in epsilon, then what we get is that the optimal probability of error is at most q to the 1 over log q, right? Using our best knowledge, our best bounds for this k epsilon from before, we get q to the 1 over log q. This is really nice, right? This is, first of all, it's independent of n. This is not that surprising anymore. The size of the tree doesn't matter in the probability of error. Remember, the trivial lower bound was q half. Okay, and if you think about, sorry, this should be log 1 over q. Okay, so if q is small, this is almost linear, but not quite. For preferential attachment, we get much worse because our best algorithm was much worse. Okay. Now the question is, can we do better? All right. Now here the idea is that we really don't need. What we need is not a small set that contains Adam. What we need is a set that is somebody that is close to Adam. Okay. So now the question is, can we find a vertex that is close to the root? Okay. And this vertex doesn't have to be maybe okay. So suppose that with some method we can find a vertex whose distance to the root is small. Okay, but of course this is a random variable. Okay, this is the output of our algorithm. Then you can easily see that the probability. What's the probability that the color of that vertex is different from the root? Well, what happens? Well, the number of color changes on the path between the root and our vertex is just a binomial random variable. There are d chances. That's the distance, right? D chances of changing color. Each one happens with probability q, and the colors will be different if this binomial is an odd number. Okay, and so this you can upper bound very easily. This is just the probability of color change is q times the expected value of the distance. Okay, so if we can find a method that outputs a vertex whose expected distance to the root is a constant, then we have constant times q as a probability of error, which is the optimum. We know q half is a trivial lower bound. Okay, so can we find a vertex that's close to the root? Okay, and yes, we can. We can go back to our favorite vertex, the centroid. Okay, the centroid will be the distance of the centroid to the root is bounded by an exponential random variable. So, in other words, the probability that with probability at least 1 minus epsilon, the the distance of the centroid and the root is bounded by log 1 minus epsilon. Okay? Equivalently, the probability that the distance is bigger than x is at most e to the minus constant times x. Okay? So it's kind of it has a nice exponential tail, and then of course, this of course implies that the probability that the expected value of the distance is bounded by a constant. Okay. All right. So how do we prove this? Well, again, this is Poiarens, right? Because for a vertex that comes at time t to be more central than the root, it must be. So if this guy is more central than the root, then it must be the case that here we have at least n½ vertices, right? This was our, right? If this is the central vertex, then we have n½ vertices here, n½ vertices here, okay? But by the time this vertex is born, there are at least t vertices here, okay? And then we have a polyiron that starts, so vertex 1 starts with a big head start, right? The number of balls here, number of vertices here, and the number of vertices here is again a polyiron, where at the beginning you start with at least t red balls and just 1 blue ball, okay? And then you can prove that the probability that this will win after n steps is exponentially small, okay? And that gives you the bound that we need. Okay, so it's again a simple polyiron argument. All right. So what we get from here is that the probability of error of the optimal rule is now between q and half, and the c is 10 or something like that. Okay, 10 times q. So it is linear. Moreover, whenever q is less than 1/2. The optimal probability of error is strictly less than 1/2. Okay, so we do better than by picking the centroid, and so our algorithm is to take the centroid and take the color of the centroid. Okay, that's really simple, and that will be better than random guessing, no matter what q is, as long as it's strictly smaller than 1/2. Okay, and nicely, this whole thing works also for preferential attachment. So there's no difference here. Okay, right? Because we don't care now that Adam remains a leaf for a long time. All we care about is to find a vertex that's close to Adam, and that is still possible by the same method. Okay, so here with this method we can get this linear probability of error both for uniform and preferential attachment. Okay. Now, what happens if in the harder version, when only the leaves are observed? Exactly the same. The exact same bounds. The exact same bounds hold. Okay. Why? Because in both of these models there exist leaves that are close to the root. Okay. So in the uniform random recursive tree, the number of children of the root that are leaves is like a Poisson 1 random variable. Okay, so with a positive probability, it has a neighbor that's a leaf, but with big probability, there will be at least one leaf within distance 2. Okay, so that means that the algorithm is just the following: find the centroid of the graph of the tree, and pick the nearest leaf to it, and take the color of it, and that will work with the same probability. Okay, so it's nice that even this harder version, when only the leaves are observed, the same bounds are available. Okay. Now you may ask, what happens if we just count red and blue balls? That's even simpler. It turns out that's not a bad idea. So it will actually work. So just take the majority vote, and this will work up to a point. So if q, first of all, we get this, that the probability of error for small q is bounded by a linear function of q. Okay? And this will work, but it's not true anymore that the probability of error is better than random guessing. Okay? It's better than random guessing as long as q is less than 1/4. Okay? But when q is bigger than 1/4, then majority doesn't matter. That doesn't work anymore. Okay? I have no time to talk about the proof of this, but now you can also ask, when can we do better than random guessing? Okay? And here, here there's a small difference between what happens when all the colors of the tree are all vertex colors are observed, or when only the leaf colors are observed. Okay, so let's look at what happens when we can observe all colors of all vertices. Okay, then we can do better than random guessing always, except when the probability of change is actually 100%, because then the colors alternate. Right? Adam is blue, Eve is red, but then from that moment on, they are indistinguishable. Right? So when q equals 1, then of course we cannot do anything. But even when q is greater than 1/2, we can still do better than random guessing, and that's a separate argument that again I don't have time to show. Okay? When only the leaf colors are observable, then we can do better than random guessing if q is either between 0 and 1/2, or it's between 1/2 and 1. Of course, 0 is included. 1/2 is not included. 1/2 is a special case, right? If the probability of changing a color is 1/2, that means that the colors of all vertices are just random, completely random. When everything is observable, then we can still use our finding Adam algorithm to localize Adam, and now what we have is just a constant number of vertices with random colors, except for one, Adam, who has the right color. So it's a little bit biased binomial, okay? And that we can use to do better. But the probability that the root is actually a leaf, that goes to 0. Okay? So if you don't observe the leaf, then there's nothing we can do when the probability of change is actually q. Okay? But when it's bigger than q, then we can still do it. All right. So this was it. Let me just put on one slide with related work. So one of the first papers that dealt with this kind of models was by Schach and Zaman. They looked at a diffusion model. When you start with an infinite regular tree, let's say a 3 regular tree, put a rumor at the vertex, and now the rumor spreads to a random neighbor. Okay, and now what you observe is the subtree of this infinite regular tree where the rumor has arrived, and then you want to find who started it. Okay, Pauling Low and Varun Jog they proved in the uniform attachment model. They proved this very nice result that says that if you look at the centroid, the most central node, our favorite vertex, that is persistent. So what that means is that the most central node eventually remains the same. Okay, so there's a random finite time at which such that beyond that time it never changes. The identity of the vertex that is the most central vertex. Okay. These papers, Bubek, Eldan, Mossel, and Ratz, and Kurian, Ducan, Korczemski, and Manolescu, they looked at if these trees are started from some kind of initial configuration. Okay, so let's say I'm asking you. So we grew a tree, and you know that it either started from a little star or from a little path. Okay, question is, can you tell? Is there a statistical test that can tell them apart? And then they proved that the answer is yes. You can do better than random guessing, no matter what. Okay. in both of these models, uniform and preferential attachment model. These papers deal with finding the seed tree. So when we know that we don't start from one vertex, but from some kind of tree. So up to what extent can you actually identify? Can you find that seed? Okay. And the broadcasting problem on trees, this has been looked at originally for regular binary trees, and then you, of course, you only observe what happens at the leaves, and then this has been extended, and there's a large. I just put in some representative papers here. Okay, thanks so much. That's all. Is there an intuition of what happens at 1/4? It's a little bit technical. So what happens is that the reason the majority works is that initially, so what you have Adam, and then some tree grows out of it, right? That has the same color of Adam, and then things change, and so when Q is smaller than 1/4, then this initial tree has enough signal. That signal kills the noise that comes later, right? And that just happens to be the threshold. Yeah. Yeah.
So the rumor spreading on the last slide, we said there's like this rumor.
Mm-hmm.
Yes, yours is the same problem, but the graph's complete.
It is the same problem, except that.
Like your underlying networks are.
Well, we look at this. Why is this?
Like, have they studied the finding Adam?
They studied the finding Adam problem exactly but on these diffusion models.
And you get these same like
They do. Yeah. Well, depends. So it depends, right? If you're in just one dimension, right? If you're aligned, then you can't do it because that's easy to see, right? Because you can either attach to the left or to the right. And then there will be a root n window that you can't identify. Okay. But if it's a random 3 regular tree, then you can already nail it down. Okay?
So I also want to ask about open problems. Like what are
Yeah. Here. So, there are, of course, other tree models that you can analyze. Some of them are actually probably more relevant than what we're looking at, like phylogenetic trees, when really these are binary trees that somehow model how evolution works, and then you want to say something. You want to find Adam. Okay. And to me, the big nice question is how up to what extent can we go beyond trees? Okay, but of course, in many cases, when you have social networks, what you observe is not a tree, but you have some network, which, like preferential attachment networks. You can have a grid or something of that sort, some growth model. To what extent can you say something? So that's, to me, that's a big, open, nice question. I'm not aware. You have to be careful how you ask, how do you formulate the question, right? For example, for preferential attachment networks, typically the way these are grown is they say, okay, start with a click, and but of course, if you start with a click, then you can just see it from a kilometer. That's very easy to find because that is not going to happen anywhere else. So you have to be careful how you set up the problem to avoid trivialities. But there are some nice natural questions. But these are hard. This could be harder.